X-ray vision from the sky at night.
This is the latest European space mission, once known as XMM, and now called Newton in honour of the great Sir Isaac. This is an X-ray satellite, and already it's sending back amazing data. Good evening. During this program, we'll be discussing X-ray astronomy in general and Newton in particular. But first, one interesting news item. The space probe NEAR, now named in honour of Gene Shoemaker, is going round the tiny asteroid Eros and sending back close-range pictures. Eros, a weird world, less than 10 miles long, irregularly shaped, and here you see the changing aspects as NEAR goes round. Features there down to a little as 600 feet in diameter. Those, I think you'll agree, are amazing pictures. You can even see bright streaks on the interior and wall of that crater, which is nearly 3.5 miles across. And now, on to our main theme. X-ray astronomy is a very young science, but already it's providing vital information. At this stage, I'm delighted to welcome Professor Martin Ward, Director of X-ray Astronomy at the University of Leicester. Martin, welcome to the Sky at Night.
Thank you.
First of all, how did X-ray astronomy really begin?
Well, if I can put it in the broader picture, visible astronomy has been around for a very long time as an organised pursuit. In fact, it's been called the second oldest profession. Astronomers have been cataloguing the positions and the magnitudes of stars for thousands of years. The big leap forward came with the invention of the telescope a few hundred years ago. Yeah. Coming more up to date, radio astronomy has been going for more than 50 years, and now we have major facilities such as Jodrell Bank near Manchester.
Lovell telescope, yes.
Yes. X-ray astronomy has only really been going for a few decades. I suppose it began as a spin-off from the peace dividend from World War II, where some of the captured German V-2 rockets were equipped with crude X-ray detectors and fired on short-duration flights to observe the very brightest sources. Now, if I was to go and build a state-of-the-art X-ray telescope plus a camera and take it out into a field and point it up in a clear night sky, I'd see precisely nothing at all. And the reason for this is that the X-rays we're trying to detect come from very far away, and they can be stopped by the equivalent of just a couple of sheets of paper. Now, of course, there's no sheets of paper between us and the objects we're looking at, but the blanket of the atmosphere, which protects us from harmful radiation, is equivalent to an encyclopedia's worth of sheets of paper. So this is why there is no chance at all of doing X-ray astronomy from the ground.
When we think about X-rays, I think our minds turn to hospitals and broken bones. Of course, X-ray astronomy is not like that a bit. We are not generating X-rays, we are picking up X-rays coming from the sky.
That's right. X-rays are part of the electromagnetic spectrum. Of course, we're familiar with light as a part of that spectrum, and Sir Isaac Newton showed how light could be split up into its constituent parts from white light into the colours of the rainbow. If we put this visible spectrum in the context of the whole electromagnetic spectrum, we see it fits somewhere in the middle, but it's actually a very small region. At longer wavelengths we have infrared, and then further still at longer wavelengths we have the radio. At the shorter wavelengths, we have ultraviolet, X-rays, and then gamma rays. So it fits in as part of the global picture of electromagnetic radiation. If we look at the universe in different wavelengths, we see different things. A down-to-earth example might be a building. Yes. If we look at that in infrared light, we would see essentially the heat being emitted. And then we look at it in visible light. Of course, this is the most familiar wavelength for us to observe. And then if we looked at it in ultraviolet, we would see something quite different again. Now, if we turn to an example in space, in the sky, if we looked at the Orion constellation, which most of us are familiar with, I'm sure, yes. We see here an optical picture with the famous stars.
Yes, the red giant Betelgeuse, upper left, the white supergiant Rigel, lower right, the three stars of the belt. Below the belt, the Sword, actually a gaseous nebula where stars are being born.
Exactly. Now, if we look at an X-ray image of that same constellation, we see something quite different. Those old favourite bright stars have disappeared because they're not shining brightly in X-rays. But many other objects, a wealth of other objects, have appeared because they're much brighter with respect to their visible light.
Well, people may say, Why study X-rays from space, and what does X-ray astronomy tell us?
And it's a good question, because we know we can build large telescopes on Earth and put them on good sites such as Hawaii. So why go to the bother and expense of building complicated X-ray telescopes? And the answer is that we want to boldly see where no one has seen before. When we look up at the sky, we might think that it's a calm and tranquil place, but actually there are regions within the universe where the densities are really high and extreme, and also of extremely high temperature. Yes. These regions are the ones that will be emitting strongly in X-rays. To give a few examples, binary stars, which you discussed in your previous program,
yes.
These systems have one star from which gas is being attracted by gravitational pull to the other star, and it's forming what we call an accretion disk. As that gas travels around the disk and spirals into the center, it becomes extremely hot, and it's these hot regions which are emitting X-rays. On a grander, larger scale, galaxies, such as this spiral galaxy we see here, occasionally harbor very interesting objects, massive black holes. They're a little bit like the binary systems, except everything is scaled up. The accretion disk is much bigger. The black hole could be 1 billion times the mass of the sun. Now, as the material spirals into this massive black hole, the lines which are emitted in the spectrum become distorted by relativistic effects. And by studying their shapes, astronomers can determine the mass of the black hole and whether it's spinning. And a third example would be a supernova, a very dramatic event, an explosion of a star. Some period after the supernova has occurred, there will be a very hot shell of gas surrounding it. This shell of gas will be emitting strongly in X-rays, as we can see here in the example of Cassiopeia A.
Well, Newton is safely in orbit and working very well. But it's not the only X-ray satellite. The Americans have a new one called Chandra, after the Indian astronomer Chandrasekhar, and that's also working well. But Chandra and Newton are not doing exactly the same thing.
That's right, and indeed if they were doing the same thing, questions might be asked as to why we need 2 satellites. The difference is that they're optimized to be very good at different areas of X-ray astronomy. The Chandra satellite is optimized to produce the sharpest images in the X-rays. Let's look at an example. Here's an optical picture of the Crab Nebula. Now for comparison, we'll look at the best X-ray image prior to the launch of Chandra. We can see here a bright source at the center surrounded by some faint nebulosity. Now if we look at the Chandra image, I think it's dramatic how much more detail we can see here. You get the impression of swirling gas, and also, very interestingly, these jets which appear to be emanating from the central region. Study of these jets will tell us a lot about the processes occurring near the pulsar at the center. Now that's Chandra. XMM, on the other hand, doesn't produce quite such fine quality images, but it is extremely sensitive, and this is very important. Perhaps I could give you an analogy. If we wanted to obtain a spectrum in X-rays, then we'd have to split the X-ray region up into its colors, much the same as the optical rainbow colors. Now if we had, let's say, 1,000 photons collected from this distant source in X-rays, and we split them into 100 X-ray colors, then we have on average about 10 photons per color. And that's just about enough to do some detailed analysis to tell us some interesting things about the source. If we had a smaller X-ray telescope, less sensitivity, we might only collect 100 X-ray photons, and splitting these up into 100 colors wouldn't give us enough information to do anything very useful. And so Chandra is optimized for the best pictures, and XMM-Newton is optimized for the best sensitivity spectra. Perhaps there's an analogy here in the sporting domain. Think of a basketball player and a jockey. Very different sports and very different characteristics required for those sports, but they're both good at them.
True enough. Well, how does Newton achieve this amazing light grasp?
That's an interesting question. Life is quite difficult for X-ray astronomers because, unlike visible band astronomers who can just make bigger and bigger mirrors, for example, the Keck telescope in Hawaii has a mirror which is 10 meters across, about the size of a living room. X-ray astronomers can't do that because the X-rays would just get absorbed in the surface of such a mirror. So we have to do something rather subtle. I have a little illustration here. So imagine this to be part of an X-ray mirror and my eyes to be X-ray detectors. So if I hold this up to me directly looking through this piece of glass, then of course there's no focusing involved. Whereas if I tilt it gradually, there's a point at which the light just glances off. And at that point, an image can be formed. Of course, this piece of glass is flat. whereas the X-ray mirror can be thought of as part of a cone with the sharp end cut off. So it's more like a bucket. Another analogy could be skimming a stone across a flat pond. If you skim the stone at exactly the right angle, which would be glancing, you could direct it to a certain point, which could be thought of as the focus. If you put it in at the wrong angle, it goes straight down into the water. The illustration shows what happens to X-rays that come in at the wrong angle. They are absorbed by the X-ray telescope, whereas when they come in at exactly the grazing incidence angle, then they can be focused to a point and produce an image. The next thing we'd like to do is to increase the X-ray gathering power of the mirror modules. And one way to do this is to insert a number of modules, one inside the other, a bit like Russian dolls. And in fact, there are 58 such mirrors, one next to the other, about 1 millimetre apart, in each one of the X-ray telescopes aboard Newton, of which there are 3. So it's a very powerful instrument indeed.
It's also very complex, and Britain is heavily involved here.
I'm pleased to say that we are. Newton is, of course, just one satellite of the European Space Agency's research programme. What normally happens is that the member states of ESA are involved to a greater or lesser degree in each satellite. And because of the heritage of the UK in the field of X-ray astronomy, going back to the very early days, we have a major involvement. And 3 university groups at Leicester, the Mullard Space Science Laboratory and Birmingham have all done a lot of work on construction of the instruments. In addition to that, Leicester University will be the centre where the data from the satellite is processed in such a way that the astronomers can actually analyse the images and spectra.
Right, Martin. Now, please, can you show us some of the early results?
Yes. Well, XMM-Newton was launched in December of last year, so it's been around for a few months. We're still checking out the instruments, calibrating them to make sure we can understand the energies of the X-rays that we receive. But as a sort of aperitif to the feast of data we hope we're going to receive over the next 10 years or so, we've taken a few images of astrophysically interesting objects. And here's one such. It's the Large Magellanic Cloud. This is an X-ray image, so the colours represent the temperatures. Blue represents very hot, and red represents cooler. This is, of course, a relative term, because cooler in this context still may mean millions of degrees. So here's the Magellanic Cloud. Up in the top left-hand corner is the region of 30 Doradus.
The Tarantula Nebula, 170,000 light-years away.
That's right. And what's very nice about this image is it's a snapshot of stellar evolution. We have the young region of 30 Doradus, and then we have a supernova down at the bottom right, circled here, which is SN 1987A.
Yes, we did plenty of programmes about that earlier on, when it was visible with the naked eye.
A very interesting source.
Indeed.
Well, that's only about 14 years old. Somewhere towards the middle of the image, the rather bright white region with a line going through it, which actually is an artifact, is another supernova remnant, but this time it's thousands of years old. And just to complete the snapshot of supernova remnants, we can see what looks like a shell of gas shining in blue light in this picture. And this is a remnant which we hadn't really been able to study before, but because of the sensitivity of Newton, we can now see the full glory of this nebula, and we'll be able to analyse the chemical composition. This is very important because the iron in our blood, the carbon and the oxygen of which we're made, was originally fabricated at the centres of stars, which became supernovae, and then eventually threw out the material which came back to form solar systems and Earth-like planets, and, of course, us. So in a very real sense, we are stardust.
Well, that's certainly a promising start. What can you show us next?
Next, let's look at something much further away. This is a group of galaxies called the Hixon Group, after its discoverer. A unique thing about Newton is that it carries on board, next to the X-ray telescopes, a small optical telescope with a mirror only about 30 centimetres across. But it's very useful to have this information, optical and ultraviolet, to compare with the X-ray emission, because it can give us a clue as to the origin of the X-rays. So in the first image of this group of galaxies, which incidentally is much further away than the Magellanic Clouds, about 200 million light-years, we see here this small group, including spiral arms, there's about 4 galaxies we can clearly see, and a bright star down at the bottom right. Now if we look at the X-ray image, the same region, we can see the star has apparently just disappeared. This is because it's not shining brightly in X-rays. But the galaxies, of course, are still visible very clearly. But perhaps the most information is to be gleaned by looking at the next picture, which is shown in X-ray colours, like an X-ray spectrum. Now here again, the blue colours represent very hot regions, and the yellow and red regions somewhat less hot. So what we can see here is a bright blue galaxy on the right-hand side of the image. This tells us, with a bit of analysis, that inside this galaxy there is a hidden quasar that we couldn't see by other means. Right next to it, just to the left, there is another galaxy which is a bit fuzzy. And the fuzziness is extremely interesting. It's indicative of a huge wind being expelled from this galaxy of a whole galactic size scale, and this is emitting strongly in X-rays. The third thing I'd like to mention is you can see a number of what look like fuzzy areas, blobs. What we believe these to be are distant galaxies, much further away than the Hixon Group. And we'd like to know exactly what these are. Because of the sensitivity of Newton, it's possible to get X-ray spectra of these objects. And when combined with some observations from our optical colleagues using large telescopes, we should be able to find out how far away they are and exactly what's causing the X-ray emission.
Well, we have Newton, we have Chandra. What about long-term planning?
Yes, well, it sounds as if we're never satisfied. Here we have two major X-ray observatories that will produce data for the next 10 years, but still it's in the nature of exploration that we want to see fainter objects further back into the early periods of the universe. And we have a problem here, and that is that we can't launch individual X-ray satellites much bigger than Chandra or Newton. So the solution to this problem has to be something rather different. The European Space Agency is currently studying a concept called XEUS. This is a very clever idea because the plan is to use the International Space Station as a platform and to assemble a large X-ray mirror in segments, much like the petals of a flower. In this way, we can make it much bigger and therefore more sensitive to X-rays than would be possible by launching an individual mirror. One other rather clever point from XEUS is that we can have the two modules, that's the mirror and the X-ray camera, as separate units, because after all in space things are weightless and there's no need therefore to have them connected by struts. Therefore we can have them flying apart as long as we can keep them a correct distance apart. The idea with XEUS is that because it will be so much more powerful than Chandra or Newton, that we'll be able to see back to the very early epochs of the universe when the first black holes were formed.
Well, Martin, X-ray astronomy may be a young science, but it has certainly come of age. By now, it's sending information we couldn't possibly have in any other way. Martin, thank you very much. Don't forget, it's newsletter time. If you want your newsletter, then send your stamped addressed envelope to newsletter number 77, The Sky at Night, BBC TV, London, W12 7TS. You can tune into our website, www.bbc.co.uk/Sky at Night, or, of course, CFAX page 620. And when I come back next month, I'm going to be joined by Dr. John Mason, and we're going to discuss the planetary conjunction due early next May. So until then, good night.